Human-Interpretable Uncertainty Explanations for Point Cloud Registration, GPCA. In this work, we develop a novel approach, which not only quantifies registration uncertainty but also explains it by attributing uncertainty to well-known sources of errors in registration problems. The most common error sources are noise, jitter, and outliers confuse correspondences, which raises uncertainty. Pose error, a poor initial guess skews the alignment, causing ICP to get stuck. Occlusion or low overlap, when there's too little shared geometry, the matches become unreliable. Traditional probabilistic pipelines quantify uncertainty, but they often fail to explain why it failed. We introduce GPCA, moving from uncertainty to actionable insights. Here's how it works step by step. First, the robot collects data through its sensors, which produce point clouds of the surrounding. These point clouds are then aligned using ICP. Next, a DGCNN embedding converts the aligned clouds into a compact, learned representation that captures geometric patterns. This representation is passed to a Gaussian process classifier, which provides both predictions and uncertainty estimates. The classifier outputs concept scores, showing how much each factor, noise, pose error, or occlusion contributed to registration uncertainty. An active learning loop can use the uncertainty values to collect new data and discover previously unseen sources of uncertainty. Based on the concept scores, we can then suggest potential strategies for addressing the issues they reveal. If overall uncertainty is high, we use active learning to collect more data and learn new concepts. If there's a pose issue, we could reinitialize ICP. If there's a high overlap score, we could change the viewpoint. And if there's a high noise score, we could filter or recalibrate the sensors. Now, let's look at a demonstration to see how this works in practice. A robot aims to grasp a mustard bottle. In the current scene, the bottle is partially occluded by a cracker box, making it difficult for the perception system to see the full object. So what should we do? We start by running GPCA on the point cloud registration. The system outputs the following concept scores: noise score 0.21, pose error score 0.13, occlusion score 0.70. Here we can clearly see that occlusion has the highest score, indicating that this is the primary cause of the registration uncertainty. This explains why the overall uncertainty was high and tells us how to act. Based on this explanation, the robot chooses a mitigation strategy. It changes its viewpoint to get a clearer look at the bottle, then rechecks the registration. With the new view, the point clouds align correctly and the registration succeeds. The robot now has a reliable pose estimate for the mustard bottle, enabling it to confidently execute, for example, a grasping task. For more information and technical details, check out our paper, and thank you for watching.